Stoichiometry. It's the measure of how much stuff you make and how much you use to make that stuff. It's a chemical recipe. In our chemical recipe, all of our units will be in the units of moles, which presents a problem. The problem is that chemistry is a practical subject. We measure in masses. This is something we can weigh out, measure in the lab. But chemistry occurs on an atom-to-atom basis, a molecule-to-molecule basis. And the way we count things in large numbers is in moles. So chemistry is occurring in moles, but we can only measure in masses. So we're going to have to do some math. And math will allow us to convert between the various amounts in calculating how much stuff we made and how much got used. We're going to get molar masses from the periodic table, and we will calculate mole-to-mole ratios from making balanced equations. All right, so periodic table, balanced equation. Periodic table, balanced equation. And that will allow us to work in moles instead of grams, eggs, cups, other things. Anyways, so said another way, if this helps the concept stick, chemistry is often known as a central science. And what is the central unit of the central science? It's moles, right? Moles are your central unit of chemistry. It's the common currency of chemistry. So this is how we do it. This is the conversion train. There are 4 stations on the conversion train, and you may not need to go to all stations. If you have grams of substance, we'll call it A, and all they asked for was the moles, then you would just stop right here. If you had moles of A and you had to calculate moles of B, all you would have to be is right here. Okay, if you had moles of that, you need to go to moles of B and then grams, so on and so forth. Okay, but a lot of the times, especially when you're doing lab work, is you'll measure some starting amount in grams, and you're going to have to figure out how much of the product or some other reactant, reagent you made or used, letter B. You're going to have to go grams to moles to moles to grams. Grams to moles to moles to grams. All right, so this is how you do it. 3 steps involved. First is a molar mass from the periodic table, which I show in purple here to go from grams of A to moles of A. In that case, you'll have the flipped version of the molar mass in order to cancel out the units properly. I'll show that in example. All right, to go from moles to moles, this will use the new concept of the video, something called the mole-to-mole ratio, or some people just call it the mole ratio. This comes from the balanced equation. We're going to be using those coefficients in the balanced equation. This is the only place you'll ever use coefficients. And then lastly, you would do a molar mass again if you had to go from moles to grams. Okay, and the units there would be grams over moles. Okay, so moles over grams, moles over moles, grams over moles. All right, we'll be seeing this throughout the video. All right, so let's get into the example for today. One example only today, because this will take up enough time. All right, so here's the scenario. We have 100.0 grams of propane gas, C3H8, and it's fully combusted, which means we're going to have high oxygen conditions, making only CO2 and water vapor. So they're asking us how much O2 is needed, how much carbon dioxide is produced, how much water is produced. All right, and we're going to break this into steps. Sometimes they'll ask you just for the moles, or more often they'll ask you just for the grams. But let's do it both ways, and I'm going to show you 2 approaches for this. One is going to be kind of a one calculation at a time approach, where we just do everything in moles first. Okay, and secondly, we'll convert all those moles into grams. We'll do a percent yield calculation later. This is like part 1 of the video. And before that percent yield calculation, I'll show another way of doing the moles and grams kind of all in one step, or the moles to grams all in one step. And I'll let you decide which way you like to work. Math is math. You'll get the same answer, so I'll let you decide. All right, let's start. The first thing to do is to make a balanced equation. Make a balanced equation. Often in chemistry, the first things you do is make your balanced equation and then convert everything into moles. When in doubt, make balanced equations, convert everything to moles. All right, so that's exactly what we're going to do here to start out. All right, so let's write a balanced equation. C3H8. Sure, we'll put the phase labels. Not crucial for today's example, but just to be thorough. And notice I like to leave a little bit of space for potential coefficients. All right, this is complete combustion, which means we are making the products of carbon dioxide gas and water vapor. All right, I teach water as a vapor in combustion reactions. I know some that will teach a liquid because eventually it'll condense back into a liquid, but we'll just do gas here. All right, let's balance this equation. So 3 carbons, meaning we're going to need 3 CO2s here. 8 hydrogens, so I'll put a 4 here to get the 8 hydrogens. All right, so when it comes to combustion, just get your carbons and hydrogens done first, and then save the oxygens for last, most importantly. And it's easier if you count the product oxygens first. So 3 times 2, and then 4 times 1, we'll have 6 plus 4. That'll be equal to 10 oxygens. To get 10 oxygens on this side, we don't have any oxygens in our first reactant, so we can put a 5 here. 5 times 2 will be 10 oxygens total, and this is a balanced equation. All right, to make our life easier today, I'm going to put a 1 here, and then I'm going to do some color and shape codes. For the coefficient of propane, C3H8, I'll use 1 in a black circle. For the 5 of oxygen, I will use a red box. For the 3 of carbon dioxide, I will use a green triangle. And then for the 4 of water, I will use a blue fluffy cloud. And I'll be referring to these shapes throughout the video when referencing the coefficients or the mole-to-mole ratios. All right, so here are our coefficients. Okay, these are our coefficients for mole to mole ratios. And a big reminder, these coefficients are in units of moles. They are not in units of grams. In order to convert between substances, like right here, we must be in moles. That is a common currency of chemistry. Okay, so there's our balanced equation. So we did step 1, we did our balanced equation. All right. I don't always think in steps, but some people like to think in steps. So here's your steps. So step 1 was a balanced equation. Step 2, we're going to calculate moles. And then step 3, we will calculate grams, masses. Okay, there we go. All right, so let's calculate some moles. All right, so we'll just call this page mole amounts. Let's start with C3H8. All right, they gave us 100.0 grams. So we're going to go right here in order to get moles. We have grams, so we have to go right here to go to moles. All right, we'll use a molar mass from the periodic table. All right, so here we go. 100.0 grams C3H8. All right, and then, oops, bumped the camera. We will convert that. All right, I'm going to use bracket notation. And I strongly prefer and recommend setting up your units before you even put in any numbers. Okay, so for molar mass, it's grams per mole. We need the flipped version of it so that our grams of C3H8 cancel, leaving us with just the moles. Okay, me writing things out this way is the same as people writing it out with fractions. Okay, it's the same thing. Some people use parentheses, again, means the same thing. So we need to calculate the molar mass of C3H8. All right, so let's do that. We have 3 carbons. Oops, my face is covering that, so I'll go over here. 3 carbons and then 8 hydrogens. All right, and I'll use the periodic table that we've grown used to by now, which is from ptable.com. They go mostly to 3 decimal places. I think that's probably overkill sometimes in Chem 101, but we'll just stick with it. Carbon 12.011, hydrogen 1.008. I'm running out of room a little bit, so I'll put my subtotals here. 3 times the 12 is going to be 36.033. 8 times 1.08, I think that's going to be 8.064. Oops. All right, add those two together. And we get 44.097 grams per mole. All right, the other molar masses in this video, we'll calculate them later. All right, 44.097. The 44 part is associated with the grams, so that's where we're going to put it. And that's per 1 mole. Mole always gets a 1. Except in a mole ratio, which is coming in a little bit. All right, so there's both ways of writing that. I'm going to use this notation for the remainder of this video. All right, so let's calculate. So 100 divided by 44.097, and we get 2.268. All right, sig figs, usually in these conversion problems, is sig figs in equals sig figs out. There's 4, so we use 4. Our molar masses went to 5 sig figs, so that's not going to influence things. 2.268 moles of C3H8 propane. All right. Now, this is a very important result. Okay, this is our starting amount. Okay, capital letters to emphasize. We're going to use this as our starting point for every calculation. Okay. So the reason why we use this as a starting point is this is something called our limiting reactant. Perhaps I could have emphasized this more a little earlier, but I did mention that we are working under a complete combustion with an excess of oxygen. So you have an excess of oxygen. You have enough of it around to fully react all of your propane. Okay, let me pull that equation back. Yeah, we have an excess of this. Yeah, I'll just write excess. Oh, excess is not a coefficient. There, excess. Or I'll teach you some chemical shorthand. Some people, all right, write XS, the two letters. And then by logic, the other would be our limiting reactant, limiting reagent. It's the thing that runs out, okay? And the moment you run out of something, the reaction's over. You can't make any more of it, okay? Just like making food, whatever ingredient you have in the kitchen, you once you run out of it, you can't make any more of whatever your recipe is, all right? So the point being, your limiting reactant is the most important thing in all of your calculations, right? It's going to be all other calculations, you're going to start with that limiting reactant. So it's the most important thing to find. We're going to use this as our starting point for all other calculations. All right, so we did the propane. Yeah, this video is going to take a while. It's going to take a while. We are now ready to go to the mole amount for O2. O2 moles. All right, so here's what we got to do. We got our C3H8 so far. Here, let me make like a quick checklist. All right, so let's recap what we've done so far and where we're headed. I just rewrote the balanced equation. All right, this is our limiting reactant, our most important thing. You can put a star near that if it helps. This is our excess. And we'll use this as our start for all of our calculations. All right, so they gave us 100.0 grams of that. And we converted that to, what did we do? 2.268 moles. I know I wrote the units here, but I just feel like repeating them today. And we're basically going to try to figure this out for each of these reactants and products. All right. And I said it'd be easier if we filled out all the moles first and then did all the grams second. Okay, we only have that grams here for the propane because that's what they gave us to begin with. So we're kind of going to go boink, 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 and then finish these three. All right, so let's go to moles of O2. So what we could do is we could start with 100.0 grams of C3H8 once again. We could take the molar mass of propane, get into moles. Oops, now I'm on the screen. And then we could lastly do that one more step on the conversion train. One more step of doing the mole to mole. Okay, do this and then do that. So here's our first mole to mole ratio. To do molar-mole ratios, as it says, this is where you use the balanced equation. And again, to remind you, this is the only time we use the balanced equation. In the mole ratio, we are starting with this, and we want to end up with a calculation of this, O2. So this is where I use my color and shape codes. 1 mole C3H8 for every 5 moles of O2. All right, and then we can do the calculation this way. All right, some people are more comfortable starting with the very first starting amount that was given to them, and you'll still get the correct answer. Some of you may recognize that, hey, we already did this calculation, and so can't we just start with the moles of that? Isn't that going to be faster? You're correct. You're absolutely correct. So if that's what you want to do, then we could just start with the 2.268 moles of C3H8. And then, see, that already gets us there. And then we can finish with that mole ratio. Oops, I broke my own advice. I usually write the units first. Anyways, all right, same thing. Right here, we canceled the grams, canceled the moles, left with moles of O2 here. Cancel the moles, left with moles of O2. All right, to prove my point that these are equivalent processes, I will calculate it both ways in the calculator. All right, there we go. Okay, 11.34. Moles of O2. And then we'll do it this way. 2.268 times 5, and we get 11.34 again. Now the top result had more like digits in the calculator because I didn't round anything, and so here by using an already rounded number, we're starting to introduce a tiny bit of rounding error, but at a Chem 101 level, that's not anything to worry about. If you don't like rounding error, what you can do is carry all the digits out from your calculator, or as like a happy medium between getting more accurate results but not taking forever. You could carry maybe just like 2 digits more than your sig figs. But 101, I'm totally okay with just people rounding to sig figs immediately. Anyways, this is the answer. Okay. If you're comfortable for the remaining calculations, starting with the moles of C3H8, when we get to the CO2 and the water, feel free to just start with that. But for the remainder of the video, I'm just going to start with the starting number every single time, just kind of establish that same process over and over again. But hopefully right now I gave you a few options. Sorry, I cut myself off. Okay, so back to the sheet. We had 11.34 moles here. And now we're going to go to this one, carbon dioxide. All right, so moles of CO2. All right, same starting setup as last time. Right here. It's just that the mole ratio is going to change right here. So instead of a 1:5 involving O2, we're going to do a 1, 2, 3. Not 1, 2, 3. 1, 2, 3. Never mind. Need to cancel that. And we want carbon dioxide. Okay, so molar mass was 44.097. I wish I gave myself more room. Okay, and then 1, it's always a 1. And then here's where this is a mole ratio. So like this is a molar mass. And then this is a mole to mole ratio. All right. 1 in black circle, and then we need the 3 in the green triangle. All right, calculate time. Okay, 100 times 1 times 3 divided by 44.097. That 1 we don't have to worry about, so we get 6.803. Moles of CO2. All right, one more for the moles water. I think we can do that on the same page. All right, same starting out part. Okay, we had a 1 in a black circle, and then a 4 in a blue fluffy cloud. For the water. Let me take this back off. Oh, that's much better. 9.071. Moles of water. Okay, and again, if you like to cancel your units, those canceled, leaving us with just those. And those units are what I write there. All right, so this rounds out all of our mole amounts, which is great. It's helpful, but it's not the practical units of mass of grams yet. But having done this work, it will allow us to do these calculations very quickly. What will allow us to do that quickly is calculating the molar masses. Okay, so just keep track of all the molar masses we have used or will use. We already used 44.097 grams per mole, quite a bit. Molar mass of oxygen, 32.00, but if we're using ptable.com, 15.99 times 2, you should get 31.998 grams per mole. All right, carbon dioxide, that will be that, and that again. $44.009. grams per mole. And then water, 1.08 times 2 plus a 15.999. That's going to be 18.015 grams per mole. So to calculate the grams, we're going to just take these mole amounts and multiply them by their molar masses. Moles cancel, leaving us with just grams. All right, so let me show that setup. All right, so I set up a separate sheet. I wrote these amounts down already. And now let's just multiply by those molar masses, which would be the very last part of our unit conversion train. We've done this, we've done that. Now we're doing that last part right here. Okay, we used a periodic table. So let's just do it. And again, a fresh reminder. Sorry if this feels a little bit, oh, what's the word? Preachy or something, but make sure you are actually trying these calculations so that you know where the numbers are coming from and you learn the process. Okay, it's one thing to watch these videos and makes it seem logical and easy, but it's a whole nother to try it yourself. All right, so make your time doubly productive. All right, let's do that. Slow down, Josh. 11.34. 362.9 grams of O2 used, consumed, reacted, whatever word you want to use here. All right, and then 6.803. Hey, did you notice the molar mass of carbon dioxide is like really similar to that of propane? Coincidence, I guess. All right, 299.4. Last one. 163.4. All right, so let's put these three things in. Okay, used, produced, or we can use a nicer word or a simpler word like made, whatever. Produced, made, same thing. All right, there we go. So a great way of checking your work is to consider the law of conservation of mass, or in plain English, you can't create or destroy matter. Chemistry is just a rearrangement of atoms. We have the same amount of carbon, hydrogen, and oxygen atoms on the left side as we do on the right side. We just rearrange their bonding partners, the same amount of everything. All right, so that means that the mass on the beginning side and the ending side must and will be the same. So we can check our work on that. All right, so 100.0 plus 36.29 we have 462.9 grams of reactants used. Okay, I know I said we had an excess of oxygen. We had more than 362.9 grams of oxygen floating around when we did reaction. All right, but the amount of oxygen used from the air was this amount. Okay, all right. And then we're going to do the same with this side. Okay, add these two amounts. 299.4 plus 163.4. All right, and then we get 462.8 grams. All right, now I'm like 0.1 gram short here. That's not because I violated the law of conservation of matter. I didn't destroy matter or anything. That's just calculator calculation rounding error. I didn't carry any extra digits when I did the calculations, so you're going to have rounding errors down the line. For 101 purposes, though, I usually don't have students care too much about that, and this is close enough in agreement, and we'll just say that is equal. Okay. Said another way, if I'd carried all of my digits throughout the calculations, or at least like 2, then there would have been a greater likelihood of these two numbers being equal. If I carried all the digits, then they would be exactly equal. All right, so I promised 2 more things for the video. One would be showing how to go straight to grams in one line. So I'll show that in a moment. And then, of course, we have a percent yield example calculation. Hang on. Here are the results if we use that starting amount, and in one calculation we went straight all the way to the grams of the other reactant or product for oxygen, for carbon dioxide, and for water. You can notice we used that same starting amount. We converted it using the molar mass of propane. Then we started doing different things, different mole ratios, and then those respective chemicals, different molar masses, right? And basically we got the same numbers. You can see that my rounding error was slight here, just off by 0.1, whereas here, since I contained the entire calculation, I was able to minimize the rounding error. But yeah, whether you prefer to do everything in one line versus breaking up into chunks like I did, that's really up to you. I would maybe consider this approach if all they asked for me was grams and they didn't care for any of the mole stuff, then I can just go straight to grams. But if they wanted the moles, then for sure I would have done the earlier approach where I did all the moles first and then the grams second. If you can't really decide what to do, one approach is just try it both ways, see what leads to more consistent results. Another approach is you could argue that since moles are so useful, you might as well convert everything to moles first. I think you definitely can't go wrong with that approach. Okay. One more thing I want to point out is that moles is a counting number, so it doesn't necessarily conserve between the left side and the right side. By conserve, I mean to say in more plain English, these two added up often will not equal these two added up. That's because moles is a counting number. It's not a measurement. Whereas the grams between the left side and the right side will always equal each other. All right, let's conclude this video with a percent yield problem. We'll use the same problem. Okay, part 2, percent yield. So we're doing the same reaction as we did before. We're not doing anything different. We're still starting with 100.0 grams of C3H8 propane, as it says here. So it says after we did a complete combustion, we were actually able to collect 36.9 grams of carbon dioxide. So it asks, what is our percent yield for carbon dioxide? Okay, another way you can think of percent yield, this is like a collection efficiency. That's probably, I think, the best way of putting it. You could also maybe say a reaction efficiency. The main idea here is there could be a number of things that could prevent us from making all of the getting all the carbon dioxide possible. So as we calculated earlier, if we had reacted all 100.0 grams of propane, then we would make 299.4 grams of the carbon dioxide. We also showed that here. So all the math we did so far was as if everything had gone perfectly. But think about it. All right, in order to make everything, number one, you have to react every single amount of your materials. And sometimes that's easy to do, sometimes it's not. You could have time, space, considerations. If you're in a rush or you didn't mix everything well, maybe you don't get a full reaction. Another thing is what if you didn't collect everything? Maybe whatever you're using to collect, it had a leak or something. Maybe you're transferring stuff, and as you're transferring things, you know, between beakers and whatever, you leave residues and you didn't capture all of it. So for a variety of reasons, maybe you won't get everything. So that's what I mean by like a collection efficiency. And often that's just summarized in this idea of a percent yield. So just to be clear, everything here is a theoretical maximum, okay? Everything we calculated so far were theoretical maximums. Okay, the math represents as if everything had gone perfect, all right? And these theoretical maximums are also known as theoretical yields. Okay, so everything we calculated so far today is a theoretical yield. All right, so on to the percent yield equation. Percent yield has the following formula. It's your actual yield divided by your theoretical yield. And since it's a percent, you'll multiply the final result by 100 and apply the symbol of percent to tell whoever's reading your stuff that you had multiplied by 100. All right, so just to make sure we're really on the same page here, okay, theoretical yield, this is what you calculated. Okay, this is a calculated value. Whereas the actual yield, this is something that is measured. Okay, this is measured. You can't calculate it. It's what you actually got. right? And if you're doing a word problem, then of course you didn't measure it, someone else did, and they gave you that number. Okay, so measured slash given. Okay, and that's how we calculate a percent yield. All right, so for CO2, our collection efficiency, our percent yield, our actual number was 36.9 grams of CO2. And our theoretical yield, again, we could have made a maximum of 299.4 grams. Make sure you grab the correct chemical, especially when you've been doing tons of calculations. Multiply by 100%. All right, I will have to pay attention a little bit to sig figs here. 3 sig figs over 4, meaning we're going to have just 3 sig figs in our answer. All right. Get that, multiply by 100, and 12.3. Percent was our percent yield for collecting carbon dioxide. All right, does that mean that was our percent yield for water as well? I think the short answer is probably no, because in order to collect something, there's different strategies involved depending on the substance. So I think that would probably be an unsafe assumption for the percent yield of like water. We didn't do a water here, okay? But I think 1% yield is enough. This video's gone on long enough, so yeah, I hope this helped with stoichiometry and percent yield, and it's just a recipe. Know when to use the periodic table, know when to use your mole ratios from the balanced equation. Follow that reaction train. Okay, hope this helps. Thanks for your time and attention, and have a great day. Take care.